All right, this is Pre-Calc Appendix A.1. Some skills for today. We are going to look at simplifying and evaluating radicals and rational exponents. We're going to look at reducing, factoring, and simplifying rational expressions. And we're going to review how to rationalize the denominator and exponents. This section is to help you practice manipulating expressions using skills and properties that you've learned in the past. You may be rusty. Your skills will improve by implementing a simple three-step procedure. Step 1, practice. Step 2, practice. Step 3, practice. These techniques require a lot of practice to be able to do them well. All right, so we're going to look at radicals and rational exponents and review the properties of those. Our first definition is about an nth root. It says let n be an integer greater than 1 and a and b be real numbers. If b to the nth power is equal to a, then b is called the nth root of a. If a has an nth root, the principal nth root of a will be the nth root having the same sign as a. The principal nth root of a is denoted by the radical expression written here. The positive integer n is called the index of the radical, and the number under that radical symbol is called the radicand. Now, a couple things to keep in mind. When you first learned about square roots, you learned that you couldn't square root a negative. Then you learned how to deal with that with imaginary numbers. But in this course, we're strictly looking at real numbers. So, first thing, if n is an odd number, if that index is odd, then you have exactly one real root. The issue is when it is even. When n is even, positive real numbers will have two real roots. Negative real numbers will have no real nth roots. So we're looking at this radical symbol. Okay. If there is no index listed, then we're talking about the square root. We typically don't write the little 2 in there for a square root just because it gets a little messier and it's not needed. If a is a positive real number and n is a positive even number, then we said that there are two real nth roots, and we will write them like this, one with the positive, one with the negative. And sometimes they put that together like that. All right, let's try a couple. First one, square root of 36. There is no negative in front, there's no plus minus in front, they are simply looking for the principal root, and since 36 is positive, we are looking for a positive 6. Our next one, we are taking the cube root of a fraction. You can do that by taking the cube root of each piece, and the cube root of 27 is 3, and the cube root of 8 is 2. Question C is almost identical, except there's a negative sign in there. And we said if this is odd, it's fine. You can take the root of a negative. So we are just simply going to get the same answer we had in part B, except it's negative. Question D, we're taking the fourth root of negative 625. Since this is even and this is negative, there is no solution to that. E is asking for the fifth root of 32. That would be 2, since 2 to the fifth is equal to 32. 2 would be the root. The fourth root of 625 is 5. The cube root of negative 27, we did that one up here as well, would be negative 3. And the sixth root of 64 is 2, because 2 to the sixth gives us 64. Now, you do have a root key on your calculator, so you can check some of these. However, we want you to do as much as possible without the calculators. All right, some properties of these radicals. It says let u and v be real numbers, variables or algebraic expressions, and m and n are positive integers greater than 1. We'll come back to this statement. It says we assume that all of the roots are real numbers, so we're not dealing with imaginary, and all the denominators are not 0. Okay, first property. it says if we are taking the nth root of a product, u times v, we can split that up and take the nth root of each factor individually first. Our example here, we have the square root of 75. Since 75 is not a perfect square, we typically look for factors that are. So we would split the 75 into 25 times 3, and then the square root of 25 is 5. So we end up with simplified answer of 5 root 3. The same idea happens in example 2, only difference is we are dividing instead of multiplying. We have an example, the fourth root of 96 divided by the fourth root of 6. Neither of those are perfect fourths, but if we put them together, we can divide the 96 by 6 first. We end up with 16, which does have a perfect fourth root of 2. Question 3 says if we are taking a root of a root, you can multiply those two indices and then take that final root all as one. So our example here, we are taking the square root of the cube root of 7. So multiplying the 2 times 3, that is the equivalent to saying the sixth root of 7. We're going to come back to number 4 in just a sec. Number 5 says take the nth root of u to the nth power. And they are saying that is equivalent to taking the nth root of u first and then raising it to the power. In other words, it doesn't matter if you deal with the index first, the root, or if you deal with the power first. Both will get you to the same answer. So in this example, we have the cube root of 27 squared. Well, I don't know what 27 squared is off the top of my head, but I do know that the cube root of 27 is 3. So if I do the cube root first, I can get that down to a 3, and then I know that 3 squared is 9. All right, take a look at properties 4 and 5. They look very similar. The difference here is that in example 4, we are taking the nth root of u first. And based on our earlier statement that if we are taking an even root, u would have to be a positive number. And we are assuming, like I said up here, that all of our answers are real, that they do work. So in this example 4, they are assuming that u is positive when n is an even number. So we don't have to worry about the other options happening. All right? And basically they're saying if we take the nth root of something and then raise it to the nth power, we've basically canceled each other out. So our example, the fourth root of 5 to the fourth power is just a 5. All right, for property 6, we have the nth root of u to the nth power. And you'll notice that there are two options for answers. One when n is even, and one when n is odd. The odd one is easy. You take the same kind of root as you take the power, and they cancel each other out, like we talked about in property 4. But the issue comes in when n is even, because if you take a u value to an even power, it will always be positive. All right, whether you started out negative or not, it's always going to come out positive. Then when we try to take the even root of that positive number, we can do it, but we're always going to get the positive version out. That's why we have the absolute value bars around the u. So we need absolute value bars if you're taking something to a power and then turning around and taking its same root, and that root is even. All right. In our example, we have negative 6 being squared, which would turn it into a positive 36. So that when we take its square root, we do have to come out with the positive 6 answer. Whereas when n is odd, like in the cube root of negative 6 cubed, cubing negative 6 does not make it positive. It keeps it still negative. So we can take the cube root of that negative value and get back to where we started with negative 6. All right, simplifying radical expressions. You must know how to simplify radicals involving algebraic expressions and for numerical computations when you need exact answers. We often look for exact answers in this at pre-calc level. Remove factors from under the radical according to those rules that we just talked about. So our first example, we're looking for the fourth root of 80. 80 is not a perfect fourth, but we can split it up. All right, we can use that first property that says I can change that 80 and think of it as 16 times 5 and take the fourth root of each of those separately. The fourth root of 16 is just a 2. So we have 2 times the fourth root of 5. That is the simplified radical version. Part B, the square root of 18x to the 5th. We can split 18 up into 9 and 2. We still have the square root of x to the 5th that we'll deal with. The square root of 9 is 3. The square root of 2 is the square root of 2. We can't do anything to simplify that. Now in terms of the x's, remember that when you're taking a root, in this case the index is 2, you are looking for groups of 2. So if we have 5 x's, think of it as x squared times x squared times x. We can group them as 2's because the square root of x squared is just x. The square root of that x squared is just x. And then we're going to have 1 that's stuck inside. So we still have one x that's inside that square root symbol, and then the other 2 x's that we were able to pull out would be in front. All right, part C, the fourth root of x to the 4th, y to the 4th. This is a case using that property 6, where we are taking the even root of something that was raised to an even power. They cancel each other out, but we have to make sure that both x and y come out as positive values, so we would need those absolute value symbols. Part D, we want the cube root of negative 24y to the 6th. 24 is not perfect, but we can split it into a negative 8 and a 3, and then we can take the cube root as well of that y to the 6th. So the cube root of negative 8 is negative 2. Remember, we are able to take odd roots of negatives. We still have the cube root of 3 left. Can't simplify that. And the cube root of y to the 6th. Since our index is 3, we're trying to take those 6 y's and group them in groups of 3, which gives us 2 nice perfect groups. All right, let's review rationalizing the denominator. It's the process of rewriting fractions that contain radicals so that there are no radicals still left in the denominator. Now this is your book's version of explaining that. But basically, if we have an uneven number of groups, all right, in other words, where we might be able to pull some of those v's out, but not all of them, we need to multiply in some extra v's to make it so that it comes out perfect, all right? We want those to come out with no radical symbol at the end. All right, so looking at our first example, we are taking the square root of 2/3. Neither 2 or 3 are perfect squares, so we can't simplify them that way. We can split it apart, but we can't leave that square root of 3 in the denominator. If we simply multiply in one more root 3, we have now turned the denominator into the square root of 9, which is a nice perfect one, and we end up with just a plain 3 for our denominator. Numerator, we have the square root of 2 times the square root of 3, which would be the square root of 6. For part B, we have the fourth root of x in the denominator. We need 4 x's in the denominator in order to take the fourth root of it. So we are going to have to multiply in 3 more. And remember that whatever we do to the denominator, we have to do to the numerator as well. This is going to give us the fourth root of x cubed in the numerator. And in the denominator, we now have the fourth root of x to the 4th that will come out with absolute values, because remember, we are taking the even root of something raised to an even power. Any negatives will disappear. Part C, we take the 5th root of x squared divided by y cubed. Remember, we are rationalizing the denominator, so we're looking at those y to the 3rd power. We have 3 y's multiplied, but we need 5 of them. So we are going to need to multiply in 2 more. All right, that gives us the 5th root of an x squared and a y squared in our numerator. For the denominator, we now have y to the 5th, and we can take its 5th root, and we just get y. There is no need for the absolute value bars since it's an odd index. Part D, we have 2 divided by the square root of 3. It's kind of similar to question A, but the 2 on top is not under a radical symbol. We would still need to rationalize by multiplying in another square root of 3. We end up with 2 square roots of 3 over the square root of 9, which is just 3. All right, go ahead and pause the video and let's try E and F on your own, and then we'll come back and check them. All right, for E, we have the cube root of x squared in the denominator. We need one more x to make that an x cubed. So we are going to multiply numerator denominator by the cube root of x. We end up with 2 times the cube root of x for our numerator. In the denominator, we now have the cube root of x cubed, which is a plain x. And for f, we have an a squared. We need 7 of them, which means we have to multiply in 5 more, giving us the 7th root of a to the 5th over an a. All right, we are going to look at rational exponents, but let's do a quick review. We've been talking about exponential expressions and when do we add powers, when do we multiply them, that type of thing. In our first example, x cubed times x to the 4th. This is a case where we add the exponents, so we end up with x to the 7th. The second one, we have a power to a power. That is a case where we multiply them, so x to the 6th. Our third example, we're back to having x to the 5th times x to the negative 2. We have to add those, and we get x to the 3rd. Our last one here is a reminder of what we do with negative exponents. Remember, we have to take their reciprocal, so we're going to end up with 1 over x squared. All right, exponents can be fractions, rational numbers. All right, think of ratio. We have x to the 1/2 times x to the 1/2. If we follow the same rule that we had up there, we add the powers, and 1/2 plus 1/2 is 1. That means x to the 1/2 times x to the 1/2 is just x. So x to the 1/2 is really just the square root of x, since the square root of x times itself gives us x. All right, our formal definition for rational exponents. It says let u be a real number, variable, or algebraic expression, and n is an integer greater than 1. This is saying u to the 1 over n is the same as the nth root of u. In other words, that denominator in this fraction is the same as what your root was. Now, if you have a number in the numerator position as well, like in this one, all right, now we have an m divided by n. The n on the bottom is still your root. All right, we've got roots here on the bottom of the tree. Bottom of the fraction is your root. The top number is your power. Think of solar power. The sun is up in the sky. So powers are on top, roots are on the bottom. So the numerator m is your power, and the denominator n is your root. Now notice in this definition, it doesn't matter if we take the root first and then the power, or if we take the power first and then the root. We still end up with the same answer. All right, couple restrictions though. That fraction exponent must be in reduced form. For example, if I said u to the 2/3, that is the same as saying the cube root of u squared. It's defined for everything. Every real number has a cube root. But if I take u to the 4/6, that is not defined for everything because only non-negative real numbers can have a 6th root taken. So it's important, even though 4/6 and 2/3 represent the same value, that we do look at it in reduced form. All right, for example 4, converting radicals to exponentials and vice versa. All right, the first one is in radical notation. All right, you see that square root symbol or cube root symbol, 5th root symbol, things like that. That's radical notation. We want to rewrite this as if it's an exponential form. In other words, we need that power and root in as a fraction exponent. So our index here is a 2, which means we have a root of 2, a square root, and we are cubing it. All right, so we have this quantity x plus y. Its power is a 3, its root is a 2. That would be another way of writing that. In part B, we have 3x times the fifth root of x squared. First thing I would do is rewrite the fifth root of x squared as x to the 2/5. And then I would look at that and say, well, it doesn't make sense to have both x's written in there. Let's combine those. This is x to the first power times x to the 2/5. We have to be able to add those. So we're going to think of that as x to the 5/5, which is equivalent to 1, times x to the 2/5. And now we have common denominators, so we can combine those and write that as 3x to the 7/5. All right, part C. These, C and D, are both already in that exponential form, and we want to write them in radical form. So we need to analyze and see what kind of root are we taking. In both cases for x and y, we look at a cube root. So we have the cube root of x squared and y to the first power. Here we are taking a negative root, so we need to flip this over, take its reciprocal, and then rewriting it, since the 2 is on the bottom, we have a square root of z cubed as the denominator. An expression involving powers is simplified if each factor appears only once. And that's an example right here where we had our x's. We don't want to have them in there twice. We want to be able to combine them. The other thing is that all exponents should be positive. Just like we had here, we didn't want to leave it that way. All right, we want to convert it so that there's no negative exponents. All right. Example 5. We have x squared y to the 9th, all being cube rooted. So instead of rewriting it as a cube root symbol, a radical symbol, we just want to make sure that each term, that x and y, both get raised to the 1/3 power. So we are going to have x being squared and then cube rooted. We have y to the 9th being cube rooted. In our second piece, we have an x and a y squared with nothing to simplify in that first step. Now we want to combine like pieces. So looking at our x's, we have x to the 2/3 and x to the first. Again, we need a common denominator to add those. Think of them as x to the 2/3 and x to the 3/3. Putting those two together will give us x to the 5/3. Looking at the y's, y to the 9/3 is just y cubed. 9 divided by 3 is 3. And then we have a y squared as the other piece, which gives us y to the 5th. All right, part B. Again, we have x's in two different spots. We'd want to put those together. We have y's in two different spots. They have different kinds of roots here. Here we have a cube root. Here we have a square root. So again, we have to think of getting those fractions to have common denominators. So looking at the top, we have 3x to the 2/3 times 2x to the negative 1/2. How can we rewrite those to have a common denominator? All right, we'd have to convert them to 6's. So we can think of this as 3x to the 4/6 times 2x to the negative 3/6. Our denominator, we said we had y to the 1/5, or sorry, 1/2, and y to the 2/5. We need to get common denominators there. We could use a 10. Y to the 5/10 would be the same as 1/2, and y to the 4/10 would be the same as the 2/5, which gives us the 3 here times the 2 would be 6. X, adding those exponents, 4/6 plus a negative 3/6 would be 1/6. On the bottom, we have y to the 5/10 plus y to the 4 times y to the 4/10. We add them, y to the 9/10. All right, our last set of examples. We need to combine radicals. In this case, notice that we are adding and subtracting, and this only can happen if we have like radicals. In other words, if I had 4 square roots of 3, I could add 5 square roots of 3, since they're both square roots of 3, and say that is 9 square roots of 3. But if they don't match, like you'll see in these examples, we have to see what we can do to get them to match. All right, so let's try to break down the square root of 80. We have 2, and instead of the square root of 80, let's think of that as 16 times 5. because 16 is a perfect square. So the square root of 16 is 4. 4 times 2 is 8. So we have 8 square roots of 5. In the second term, the square root of 125, we can break that into 25 and 5. Square root of 25 is just a plain 5. We still have the root 5 left as well. Now you look at those and they match. They both have a square root of 5, so we can actually do the subtraction. 8 square roots of 5 minus 5 square roots of 5 would be 3 square roots of 5. In part B, there's some pieces that we can pull out. For example, the square root of 4 is 2. We could simplify that. The square root of x squared is the absolute value of x. It has to come out positive. But there's still a square root of y piece on there. In the second term, we have 3 y's being multiplied under that root symbol. So we can pull out a group of 2 as 1. It's going to come out again, absolute value of y times the square root of y. All right, and now we could simplify that a little bit since they both have a square root of y in them. This piece here is what's matching. The other pieces you can think of as the coefficients, all right, which means we have 2 absolute value of x minus the absolute value of y, all being multiplied to a square root of y. All right, part C. We can simplify the square root of 36 into just a plain 6. We can start breaking down the 24. Think of it as the square root of 4 and the square root of 6, which gives us 2 square roots of 6. But that's all we can do on that one, since the first 6 there does not have a radical piece with it. That's as simplified as it could go. All right. Why don't you pause the video, try the last 3, and then we will come back and check them. All right, for question D, we can split our 24. We're looking for a perfect cube in 24. We could use 8 times 3. We're looking for a perfect cube in 81. We could use 27 and 3. All right, notice that both of them have given us a cube root of 3 as one piece. Simplifying, the cube root, one sec. All right, let's try this again. We have the cube root of 8. We can simplify that as just a plain 2, and we have the cube root of 3 left over. In the second term, the cube root of 27 is 3, and we have the cube root of 3 as its other piece. Again, both of them have a cube root of 3 part, so we can put them together. 2 plus 3 would give us 5. Part E, we want to simplify the square root of 50. Think of it as 25 times 2. Gives us 5 roots 2. For 32, we can think of that as 16 times 2, which would be 4 square roots of 2. Adding together, you should get 9 square roots of 2. And our last one, the fifth root of 96. We need a perfect fifth. So 32 is perfect. It goes in there 3 times. All right, simplifying, the fifth root of 32 is 2. We have 2 fifth roots of 3. We are adding another fifth root of 3. Think of there being a 1 in front, which gives us 3 fifth roots of 3. All right, so just to summarize, when we're simplifying radical expressions, we want to remove factors from under the radicand. All right, if there's something that we can pull out, like right here, we could pull that 25 out as a nice 5. We need to do that. We want to eliminate radicals from the denominator. That's that rationalizing piece. And then we want to combine sums and difference of radicals if possible. So if we can get them to have those matching radical parts, we want to add and subtract them to simplify. All right, your assignment is in the back of the book, page 782. You'll be working on the odds 1 through 81.